Okay, welcome to our Thanksgiving week. And this is our only session this week, Monday, November 23rd. Remember, you have no classes at all, no classes or meetings at Delta College classes, Wednesday, Thursday, or Friday of this week. So there was a request to do an example like homework problem 10C that you guys are working on for tomorrow. So I'll give you a nice example of that, and then that works into our discussion of law of cosines and area formulas for triangles. So just to make sure we're all on the same page, let's check out this week in Math 121. We're in week 13, so we're going to talk about these two sections today, but that's only session we have. Thanksgiving break. Enjoy yourself on Wednesday, Thursday, and Friday. So law of cosines and area of a triangle. You're working on homework number 10. And the following homework number 11 is posted. You're working on some sections in the XYZ homework. And then the XYZ homework sections due next week are only the two sections we're discussing today. 10 part A. That'll come with the question in 10C, so we can do that. I'll work that in somehow. Thank you, Kaden. So you're getting ready for your exam. This is week 13, and exam in week 16, pretty much the same process we used for exam previously. So I'll help you get ready for that as we get closer, but let's focus on these two homeworks you're doing in this week. Let me go back to here. And let's pull up homework number 10 since you've asked two questions on that now. Let's just look at the problem before we roll on. Yeah, so we will do an example of all three of these parts. So our motivation here is we want to solve a trigonometric equation that's a little bit messier, got sines and cosines in it at the same time. So how can we do that? How could you solve an equation like the one presented at the bottom here? Let me blow it up. How do you solve an equation that's got both sines and cosines in it? Well, if the sines and cosines have the same argument, what I could do is rewrite this equation. When I blow up my screen, it messes with the highlighting. Rewrite this equation here in terms of one sine or cosine. And that makes the bottom equation easier to solve. So let's illustrate that. Okay, so I'm going to write a formula down that looks like that problem, but not exactly like that problem. But if you follow the calculations here, you should be able to do the calculations here. Let me switch to my paper and then let's go. Let's say that instead of the one in the homework, this is the one I gave you. Now I changed a 2 to a 3 and 3 to a 2 and put in a minus sign. But it's a similar type of problem. What do we want? We want to write this as one sine wave. in particular because it might help us graph it easier. Graphing is part B. And it might help us solve an equation easier if we set this equal to a number. Well, how can you turn a sine wave and a cosine wave into a single sine wave? You have to use an identity. So the identity that comes to my mind is this identity. That if I take the sine of A, the cosine of B, and add the cosine of A and the sine of B, what I do is create, excuse me, get one more person in here. What I do, this is a sum of angles identity. It's the first sum of angles identity you learned. I create the sine of A plus B. I wrote this in a different color because I want you to say, you know, this is not what's written in red here. How am I supposed to do this? Okay, well, hang on to that for a second. First, do you acknowledge this? That I'm taking sines and cosines on one side and turning them into a single sine. That's how I'm looking at this formula. So having looked at the formula in that way, I'll go back to the red formula and say, can I make this look like that? What if I did this? What if I pretended there was a 1 there? You know, minus cosine 3x is the same as minus 1 cosine 3x. And then what if I pretended that the sine 3x was the sine of A? You know, this belonged together. And then the cosine of 3x was the cosine of A. These belong together. I'm trying to match. I got 4 people up here. 2 sine 3x, minus 1 cos 3x. I got 4 people there trying to match it to these 4 people. Well, the next thing I'll do is think about this 2. Can I match it to the cosine of B? Well, automatically, right away, that doesn't make sense because cosine can never be 2. So I'm not sure what that means yet. I'd also like to match this minus 1 to the sine of B. So at the first moment, I'm a little bit confused, like how could I make these match? So the book says this to you. This is what we did last time. Think of this problem as A sine 3x plus B sine 3x. And the A will be the 2 and the B will be minus 1. There's a negative sign there. I can't just ignore it. So B is minus 1. Could I rewrite that so that it would be legitimate to use this formula? And the book said, yes, you could rewrite it in this way. Out in front, you put A squared plus B squared square rooted. And then inside, you divide in the appropriate place by A squared plus B squared square rooted. Divide that 2 by that number. Leave the sine 3x alone. Divide the B by that number. And leave the cosine 3x alone. Now, this could be a legitimate cosine of another angle. This number is less than 1. This number is less than 1. And these 2 numbers represent the sides of a triangle. A Adjacent over hypotenuse, opposite over hypotenuse. But let's not talk about A, B. Let's not talk about green. Let's take the red thing. A is 2, B is -1. And fill this in. So now my red equation, slide this up, excuse me. My red equation becomes, I'm going to change the order here to make things neat looking. Square root of 2 squared plus -1 squared is 4 plus 1, 5, 5 rooted. So out in front here, I got a root 5. And I got the sine 3x. And then here I'll write 2 over root 5. Now you can kind of put on hold for a second, saying like, what does this do for me? I'll show you what it does for you, but first let's just rewrite it. Here I write cosine 3x. And the -1 over root 5. Now this looks very much like sine A, cosine B, cosine A, sine B. Now this looks very much like that blue formula for the sine of angle plus angle. And here, I'm talking about this other angle. Let's call this angle C. I've got an angle C whose cosine must be 2 over root 5. And whose sine must be -1 over root 5. I want to emphasize to you again that these two red equations are exactly the same, right? Even though the second one looks fancier. If you multiply by root 5 on this piece, you just get 2 sine 3x. If you multiply by root 5 on this piece, you just get minus cos 3x. So these two red equations are completely the same, just rearranged. And now I want to think of this as root 5 sine of 3x cosine of c plus cosine of 3x. Sorry, I got to slide my paper, and pretty soon I'm going to lose the stuff on the top, but you can print these out later as well, and I can go backwards. So I want to rewrite this now as root 5 times the sine of 3x plus c. And this is what the problem told you to do in part A, to rewrite it as A times the sine of bx plus c. In part A, they told you to rewrite your two-piece trig function with a one-piece trig function. I will definitely get the minus, so hang on for a second. That's a good point. First of all, I want to make you say this, that remember in the sine of a plus b, plus goes with plus. So that's a given. You have no choice. Now you say, but there's a minus sign there. So since I had to read plus sign right there, where did I put my minus sign? I snuck it onto this piece. So I still have a minus sign in the problem, but this plus sign has to become this plus sign right here. So this is just the identity saying when you do sine of A plus B, you keep plus with plus and minus with minus. What's going to happen to this minus sign right here? I'm going to have to draw a picture of this thing. I'm going to have to draw a picture of the angle C. And I'm going to have to draw a picture of the angle C with a sine, the cosine of 2 over root 5 and a sine of minus 1 over root 5. Let's draw that picture right now, since apparently we're here. So you draw me. I'm the magic hand right now. You draw me a sine, an angle C that has a cosine positive 2 over root 5 and a sine minus 2 over 5. It would look like this. 2 units for the x minus 1 unit for the y. It would be going through this point 2 and minus 1. And it would have hypotenuse of root 5. Oh, sorry, that's where I have to slide up the paper. So this right here is the angle C. It's got the right cosine, yep, 2 over root 5. It's got the right sine, 1 over root 5 negative, because I'm downwards. And this is the drawing right here. You could write this angle like this. Sine inverse of minus 1 over root 5. Or you could write it tan inverse of minus 1/2, or you could write it cosine inverse. Well, that would get trickier because cosine is coming from these two quadrants. Remember, sine inverse comes from first and fourth quadrant. That's why I picked the sine inverse here. So now we're doing part B. Think about this. I just did part A. You could put this fancy symbols in here if you want. But part B says, are you sure you're telling the truth? Part B says, why don't you graph this and show me that it's exactly the same curve? Because unless I graph this and show you that it's exactly the same as the one you began with, you're going to say, well, your work here was worthless. So let's check it out. I'll pull up Desmos in a second, but I'm just going to write down what I'm going to type into Desmos. 3x plus this fancy sine inverse of minus 1 over root 5. And to cover Austin's question in the chat, which was very important, that minus sign slid over into here. It did not go into my identity. Okay, so now I'm going to draw this. I'm going to draw the one I originally wrote up here, and they better be the same, or else I lose a lot of credibility. Or you just admit that I made a mistake. So let's go to, but I think we're on track. Let's go to Desmos. I got to get my window oriented. Desmos.com. Got it. Let's graph. Now, on my paper, I'm just reading what I made up. This is not problem 10. This is a made up version of a problem that looks like 10. So I have y equals 2 sine 3x stop minus 1 times cosine 3x stop. Now, I also just want to show you, this is first of all, it's a sine wave or a cosine wave, depending on where you look at it. But let's just look at it from 0 to 2 pi. So I'm going to run the axis in terms of 0 to 2 pi. Don't need to say minus 0. Pi over 4. I don't know, that looks nice. And you see that here in 0 to 2 pi, I have 1 wave, 2 waves, 3 full waves, but they start at a different place. They start and stop at a different place. I might pop backwards minus pi over 4 and go to 2 pi plus pi over 4, just to give you a little more view of that. It's like the sine wave started right here instead of where it naturally starts at 0. Okay, now here's the acid test. So I got to type in the one we created, which was a square root of 5. Well, let's make it y equals, let's make it dotted. And I got to fill things in as I type, sine of 3x. You notice that already has the same period. It looks like the red curve that I just did. In fact, if you were like, very, very forgiving, you'd say, oh yeah, that must be right. They look so close. But why are they not exactly the same? Because I haven't added in this phase shift determining thing. Let me add in plus sine inverse on Desmos. On your calculator, it's on your keypad. And Desmos, sine inverse is right here under the trig functions. Minus 1 divided by square root of 5. Terminate the sine inverse. Terminate the sine. This looks like I got the right number of parentheses. And the wacky thing is, do you see that this is exactly the same sine wave as the one we were given? So we were successful in turning a sine wave plus a cosine wave into one sine wave. Now, I agree, the sine wave of a mess, I had to add this other messy angle to my 3x. But I did get the exact same sine wave. Now let's look at 10C. 10C in your homework problem says, well, now why don't you use this to tell me where this messy wave is equal to 2? Let me add that. It'll be the green line. So the green line going to tell me what? Green line going to tell me where is this sine wave exactly equal to 2? And Desmos even knows where it's exactly equal to 2. And right now I'm between 0 and 2 pi. So you know what I'm going to do to both of these graphs? I'm going to restrict them so that they only go from 0 to 2 pi. So this is like an extended example, but it's kind of worth it. Let me take my two functions that I drew and I put in braces afterwards, 0 to 2 pi, and that'll cut them off. So they only get drawn from 0 to 2 pi, 3 full waves. Then I say to Desmos, draw the line y equals 2. And Desmos not only draws the line, but it'll tell me where they intersect. Notice something funny though. Sometimes Desmos thinks it knows exactly where they intersect, like pi over 6 and 2. But then sometimes Desmos is only approximating where they intersect. Why is that? Why does it know the exact answer sometimes and not the other times? Okay, well, that's why we got to do 10C. So I'm going to leave this up on the screen. Let's go back to our paper. So we're right here right now. We successfully wrote one sine wave. So how are we going to use that to solve the problem? Instead of doing 2 sine 3x minus 1 cos 3x is equal to 2, that's hard to do because I got sine wave and a cosine wave. Let's replace this. with the root 5 sine of 3x plus obnoxious shift. Now, I'm not going to say this is painless, but it is only one sine wave right there. So how do you solve this for x? Well, you carefully unwrap this equation. Got to get the root 5 over to the other side. Got to take off that sign. Once you take off the sign, you've got x still wrapped up with this 3 and sine inverse. So one step at a time. First, I divide both sides by root 5. That looks very tame, except I got to drag this monster argument along with me. Now I have to take off this sine. Say sine of this angle. Just think about this as a giant angle D. Sine of D is 2 over root 5. So I'm really saying D is the angle whose sine is 2 over root 5. How do I write that in math language? There's the big ugly D. Equals the sine inverse of 2 over root 5. Now this is almost ready for me to solve for x. Remember, that's my mission, solve for x. The problem on your homework says, solve for x to the nearest thousandth of a radian. We got to think about this picture for a second. What angle is this? The answer is, it's the angle whose sine is 2 over root 5. So I have to draw that. Because technically there's lots of angles that have a sine of 2 over root 5. Remember, sine is opposite over hypotenuse. So this could be this angle right here. Opposite side 2, hypotenuse root 5, and adjacent side with the Pythagorean theorem 1. So that's 0.2 comma 1. Sorry. 1 comma 2. But the mirror image of this across the y-axis also has the same sign. Height, or y value 2, x value minus 1, because I'm going to the left, hypotenuse root 5. The name of that point is minus 1, 2. So these two angles right here are the two choices I have for this big ugly thing I call D. I only call it D so I don't have to rewrite it over and over. I'm going to have to rewrite it sometime, but for the moment, let's just call that D. Here are my two choices. And the two choices are sine inverse of 2 over root 5. That's this smaller angle, this angle in the first quadrant. And what's its mirror image look like? Pi minus that angle. Pi minus sine inverse 2 over root 5. Remember, 2 over root 5 is a particular angle in the first quadrant. Sine inverse of 2 over root 5 is a particular angle in the first quadrant. Okay, so now we can get down to solving your problem, or solving this problem that's like your problem. So I have two chances for this angle right here. But I also have to remember I could add 2 pi, add 2 pi, add 2 pi, and the same thing to the other one, add 2 pi, add 2 pi, add 2 pi. I could have many different angles that land on these two sides. So I'm going to write the D, this monster D, is equal to sine inverse 2 over root 5 plus any multiple of 2 pi, or this monster D is equal to pi minus sine inverse of 2 over root 5 plus any 2 pi added or subtracted from that. Now this looks like a real mess, but now it's time to solve for x and to estimate these values on the calculator. Because in this problem, I did say estimate. You do need to estimate. So I'm going to subtract sine inverse of minus 1 over root 5 from both sides. That'll give me 3x is negative sine inverse minus 1 over root 5 plus sine inverse 2 over root 5 plus any number of 2 pi revolutions. And the second line says, I'm going to subtract this 1 over root 5, excuse me, that's a root 5. But I also have this pi in front, so I'm going to write pi minus sine inverse 1 over root 5. These don't look exactly the same, but they're kind of similar. Notice there's a minus sign in front of this sine inverse here. This one's got a minus sign, this one doesn't. Sine inverse here of 2 over root 5 plus k times 2 pi. Now I can tell you what x is. I divide everybody by 3, which looks bothersome, but why don't you just write a 1/3 in front of everybody? 1/3 sine inverse minus 1 over root 5. Oh, sorry, I got to slide the paper up. Plus 1/3 sine inverse 2 over root 5 plus multiply k times 2 pi by 1/3. K times 2 pi over 3. And the other possibility is divide second equation by 3, pi over 3 minus 1/3 sine inverse of minus 1 over root 5 plus 1/3. Oh, sorry, that's a minus 1/3 on this one. Sine inverse 2 over root 5 plus 1/3 of k times 2 pi, k times 2 pi over 3. Now these ugly looking numbers here, but I can ask the calculator for some of these values. Let me get out my calculator. Where did I put my calculator? It's up here. So how to show this and the calculator screen to you at the same time. I'll squeeze the calculator screen down here, which looks a little small, but let's type it in. Parentheses, minus 1/3, stop. Sine inverse. Minus 1 divided by the square root of 5. A little bit of typing here. Stop. Plus 1/3. 1 divided by 3, stop. Sine inverse, 2 over root 5. It's going to spill across the screen. Stop. Now I'll add these multiples of 2 pi over 3 manually. The first thing I want to do is make sure I'm in radian mode because they asked me for radian answers. I'm in degree mode. Let me go back to radian mode. Okay, let me see if I can raise the calculator too. Okay, raising the calculator. So quit, and now let's ask the calculator what this equals. To the nearest thousandth of a radian, 524. So now I'm going to write that in here, 0.524. But I could also add 2 pi over 3, 2 pi divided by 3. That would give me 2618. Let's try to add 2 pi over 3 again, because I haven't gone past 2 pi. 2 pi is 6.28 plus 2 pi divided by 3. Got it? 4712. So these are 3 answers. Remember in the graph we just did a second ago, we saw 6 answers. So let's get 3 answers down here. Now I'm going to have to change what I typed up here. Namely, I'm going to have to put up pi over 3 in front of it. And I still got the minus sign there. So let me insert pi over 3 plus that. Okay, good. Now I have to change this sign to a minus sign. It used to be a plus sign. Slide over there and change that to a minus sign. Good. And then that's the end of that. So what's that value? 0.833. Add 2 pi over 3 to that. $2,927. And add 2 pi over 3 to that. $5,021. Okay, I'm going to pull my calculator out of here, but what I got is 6 values of X rounded to the nearest thousandth. Now, we're just going to have to check these against the calculator. So I can't have that in the screen at the same time. Let me see. But I'll remind you what I wrote. Let's go back to our Desmo screen. And let's look at these black dots. 2nd position, 4th position, 6th position. Do you read them? 0.833, check. 2.927, check. 5.021, check. Now, I also approximated the first 3 because I didn't know any better, but Desmos is shaking me about the shoulders and saying, oh, did you know that was pi over 6? Did you know that was 5 pi over 6? Did you know that was 3 pi over 2? I did not know that, but I can check, ask the calculator what pi over 6 is and see if it matches those 3. But you see, I did find the 6 places where this is equal to 2 by rewriting this equation in a funny way. And we're going to have to leave this because we spent some time on it. We're going to have to leave it, but I think I'll do that last check. If that's actually exactly pi over 6, 5 pi over 6, 3 pi over 2. So clear screen. Is the 0.524 pi over 6? 524 if you round up. What about the 5 pi over 6? Is that 2618? My writing here is a little crowded. Sorry. 2618 rounded to the nearest thousandth. 3 pi over 2 is at 4712. So these answers are correct to the nearest thousandths. For some reason, I just got lucky and they happen to be exactly these. I don't think that happened on the problem you're doing. Okay, let's go for the big overview. Let's go back to your homework. This problem was not your homework problem. I'll cover your question in a second, Austin. You are correct, but just for the purpose of typing, it was okay for me to type the inverse sign there. But I will get to your question. That's a good observation. Let's go back to your homework problem. Where is it? Tab, me, pages, semesters, trigonometry, 13, homework 10. So you have a funny function, expand this, and we want you to turn it into just one sine wave. So that was the first step. We illustrated that using the identity for sine of a plus b. Then you could graph that function really nicely. Now I graphed it in Desmos, but you could write the phase shift and make a graph of it here on the paper. It will be an approximation. I don't mind if you use Desmos to get yourself the approximate points. Just draw a really nice picture from 0 to 2 pi, which will cover, in this case, since this is sine 2x cosine 2x, that'll cover 2 periods. So give me the amplitude, period, and phase shift there. And then use that function, just like we used ours, in place of this double trig function, sine 2x, cosine 2x, use the one you created to find out where it equals 2. And you can type the one you created into Desmos and see the numbers where it crosses to check your work. Now, just a warning, this is sine 3x and cos 3x. So that's 3 periods in 2 pi. Your problem was sine 2x, cos 2x. You're only going to have 2 periods in 2 pi. So you're not going to have 6 answers. I think you're going to have 4. But you go and work it out. This is a decently messy problem. Just, a lot of intense work here. Just to cover, before we go on, just to cover Austin's last question here. I had 2 sine 3x minus cosine 3x, and we turned it into root 5 sine 3x, one sine wave, hooray, plus sine inverse of minus 1 over root 5. Now the problem is that's not a famous angle, so I can't just call it pi over 3 or pi over 6. So I just leave it as it is. But if someone asked me for the phase shift, well, what would I have to do? I'd have to set this equal to 0. And solve by subtracting the sine inverse and dividing by 3. Now, just to show you that that actually showed up in our graph. Remember, I'm doing my problem, not your problem. Let's type in minus sine inverse of -1 divided by square root of 5. Don't need the parentheses there. Need the parentheses there. And then let's take that divided by 3. It's kind of a mess to type in. And Desmos says, I'm sorry, calculator says 0.155 to the nearest thousandth. If we go back to Desmos, I realized my paper was off screen, so I'll go back to my paper in a second. Find out where this sine wave begins. Do you see this sine wave begins at 0.155? So I could call that my phase shift approximately, but let me go back to my paper. When I write like this, I'm telling you the phase shift exactly, -1/3 sine inverse minus 1/√5. Approximately is 0.155. But this, instead of sticking a point, well, I'd have to do something else there, but I don't want to stick 0.155 in here. I wanted the exact value. Okay, so this is a pretty intense problem. One more question here. Okay, got it. Part C, you insert your function, subtract 2. I'm reading Austin's question from the chat. So you got this vertical shift with your function equal to 0, causing your sine wave to lower. Then your sine wave intersects 0 on the x-axis. You could do that, but I thought it was more direct. Let me go back to my picture. I thought it was more direct to just, let me turn one of these off, to just add the line y equals 2 in there. Let me show you what Austin was asking. What if I had just graphed this -2? So instead of saying, where does this equal to, I'll just graph this -2 and find out where it equals 0. But when you do that, I want you to see you get the same numbers as you got here. Pi over 6, 0.833. 5 pi over 6, and 2.927. The graph gets a little too busy here. 3 pi over 2, 5021. 3 pi over 2, 5021. I don't think I could, I can't get all the points on here because then Desmos just cuts out some of the points. So whether I solved where the red curve crosses the green curve or where the purple curve crosses the x-axis, I get the same answers. You could do it either way. I just thought it was easier to draw the line y equals 2 and find these places right here. Okay, that was intense. So I got some territory to cover here in a short time. Let's go on. And I'll show you what the law of cosines is. The law of cosines is like a brother or a sister to the law of sines. Let me slide my papers up. Let me number my papers so we can scan them later. The law of cosines is like a sibling, the law of sines. The law of sines says if you have a triangle, it doesn't have to be a right triangle with angles A, B, and C. and sides, A opposite A, B opposite B, C, little c opposite little c, then the ratio of sine A to little a is always the same as the ratio of sine B to little b, and it's always the same as the ratio of sine C to little c. This law of sines could be kind of like saying that this equation is the superpower of sine. If you want to think in, you know, Marvel comic universe or DC comic universe. So this rule always holds for any triangle. This is a special power of sine. A law of cosines has a special power too, and it looks different, but it's equally useful. Where is the law of sines useful? Law of sines useful if I have angle and a side opposite, because if I know one of these ratios, I can make the other two. That allows me to know the whole triangle. Law of cosines also allows me to know the whole triangle if I don't have a matching pair of angle to side. So let me draw a picture here. Relatively large picture. Let's make this A and B. Let's throw a C over here somewhere. Here's a generic triangle. And get in the habit, I don't care which one you call capital A, B, or C, but get in the habit of matching the opposite side with the same letter, lowercase. Even though capital C's and lowercase c's are sometimes hard to distinguish. What does the law of cosines do? Law of cosines is kind of like fixing the Pythagorean theorem. Now, you know the Pythagorean theorem really well. You know, if I draw it up here, triangle, ABC. Doesn't matter where I put the letters, remember. Lowercase c, lowercase b, lowercase a. You know the Pythagorean theorem says a squared plus b squared equals c squared. But that is only true for a right triangle. And so you're kind of look at this triangle right here, this general triangle, and say, you've been shut out. Like, I can't do the Pythagorean theorem on this triangle. Well, you're right. You can't do the Pythagorean theorem written like this on a triangle. But you can write something that looks very close to the Pythagorean theorem that allows you to solve this triangle. You can say that c squared is a squared plus b squared minus a little fudge factor, minus a correction. And the correction goes like this, minus 2ab cosine angle C. This is not the Pythagorean theorem. I mean, if I covered up this correction, it would be, but that's not right for this triangle. This is not a right triangle. So how can I write this? I can't write that unless I correct it. And it turns out that the correction is to subtract 2ab cosine C. But even better, I could have written it as b squared equals a squared plus c squared. That's almost the Pythagorean theorem, but then I make my correction to a c cosine b. Do you see the pattern here? Side c, cosine c. Side b, cosine b. A squared plus b squared, 2ab. A squared plus c squared, 2ac. With the law of cosines, I get 3 Pythagorean theorems. Well, okay, not Pythagorean theorems. I get 3 things that look like the Pythagorean theorem. Last one would be a squared. Write it. is b squared plus c squared. And what's the correction factor? 2bc cosine A. These three formulas. Really, it's one formula with the letters moved around, right? So this pattern, maybe I should say it that way. This pattern, or if you like, these three formulas are called, excuse me, I started paper up, the law of cosines. And this law can solve triangles that this law can't. And vice versa. The law of sines can solve triangles that the law of cosines can't. Right? So you use both of them as twins, you know, hammer, saw, brother, sister. You use both of them to solve triangles. If triangle can't be solved with the law of sines, maybe it can be solved with the law of cosines. If it can't be solved with the law of cosines, maybe it can be solved with the law of sines. Let me give you an example. So I'm going to take number of my pages here. Let me draw a triangle looking any way I want to, but remember I gave you this advice last time? Make one side horizontal, make one side on the horizon. It's just easier to manage. Put the letters anywhere I want. Let's put C, I don't know, way up here. And let's connect the triangle. Connect that side there. I try to draw a generic triangle. To me, I hope I didn't draw AB the same as BC. I think BC looks a little bit longer to me. But let's find out. Let's say that this angle right here, it's not quite 90, it's more than 60. Let's say that this angle right here is 74 degrees. And then let me give you two sides. And you say, cool, I'm going to use the law of sines. But I'm going to give you two sides in a silly way. Not useful to you. Let's make this 12.7 and let's make this 15.3. If you want to attach units, we can say feet. Now you go get the law of sines. But then you realize, wait a minute, law of sines is not going to help me because I need a pair. I need partners. And I have this angle, but I don't have this side A. I have this side, but not that angle. I have this side, but not that angle. The law of sines right here is not useful. At least not immediately. Sorry, I gotta slide this over. So why don't we draw the law of cosines? What do we know? We know A angle, we know side C, and we know side B. So look at your law of cosines. A angle, side B, side C, side B, side C. That would tell us side A. I don't know what side A is, but if I plug these things into the law of cosines, let's use A squared equals B squared plus C squared minus 2BC cosine A. Let's use that to find A. I'm going to get out my calculator, but first let me write it down. A squared is B squared, which is 12.7, plus C squared, which is 15.3, minus 2 times B, which is 12.7, times C, which is 15.3. There's going to be a lot of typing right here. Sorry, that one was squared. And now cosine of A is cosine of 74. So I'm going to find out what A is, but I have to type all this stuff in and take the square root. So let's be really careful with this. First, I'll type it all in, and then I'll get the square root, but I won't round off. I'll just take the square root of whatever I got here. So let's bring the calculator in. So this is going to be a long type, 12.7 squared. I didn't write 12.7. Try again, 12.7 squared plus 15.3 squared minus 2 times, oh, I got to use not the opposite key, but I got to use the minus, the subtraction key. 2 times, maybe parentheses are not a bad idea right here. 12.7 times 15.3. Okay, good. Now I use the parentheses here just to show you the pieces, like I wrote them down. Now I gotta do cosine 74. Now I'm in degree mode again. I think I better check because I was in radians a second ago. We'll make sure we're in degrees. You could do the calculation radians if you want, but I got 74 degrees given to me. Okay, so now I've got everybody assembled. I've got cosine of 74. I'm in degree mode. So here's A squared. 288.2618, it doesn't help me to write all these numbers down. And I don't need to, because they're on my screen. I'll just hit the square root button. Let's take the square root of that last answer. Remember, you got this key down here, the last answer key. Now you could also type in all those numbers, but I'll just take the square root of the last answer. What do I got? 16.97. Again, I don't want to use all these digits. I was doing things to the nearest tenth. Let's go to the nearest tenth. 16.9, but I got to round up, 17.0 feet. Now this is approximately. So I write on my triangle, approximately 17.0 feet. Okay. Now, notice that I thought this BC was a little bit longer. It turned out to be slightly longer. All three of these sides are close to each other, but 17.0 is a little bit longer than 15.3. Okay. Now, what's left for me to do? I still don't know what B is, and I still don't know what C is. But now I got a partner. Sine of A over A. Now I can use the law of cosines. So when I said to you at the beginning, the law of sines is not useful here immediately, that means I'm going to use it. I'm going to use it. But first I need to find a pair to work with. So I'll put this note here. And now let's come down here and use it. Now, the only thing I'm worried about is this is an approximate number. So I want to use this whole approximate number. I should be careful how I do this. But any way I do this, I'm going to have to use an approximate number. So let's write that sine of A is to A is sine 74 to 17.0, but that's approximately, right? So you could write the whole crazy number from your calculator right here. Or you could just use this whole crazy number later. I'm going to write approximately 17.0. And then, now the 12.7, 15.3 are exact. This is the sine of B over 12.7 and the sine of C over what? 15.3. So the sine of B times this approximately 17.0 cross multiply is equal to the sine of 74 times this 12.7. I squeezed that in there too tight. So what's the sine of B? 12.7 times sine of 74 over this crazy number. Okay, now's the time I'm going to use that whole crazy number from my calculator. So let's show you how to do that. I could type 12.7 times sine of 74. I'm in degrees. And now I'll divide by what? The last answer. Or I could highlight it and grab it. But I could just say the last answer. Because the last answer was the whole number, as approximate as the calculator could do it. Now that's a big number itself, right? 0.719037.9, goes on forever. But I just want the sine inverse of that number. So what's sine inverse of that crazy number? I'll just type sine inverse of answer. Sine inverse of answer. In other words, I just let the calculator keep track of these large crazy numbers and put it in the right place. In degrees, that's 45.975. What if we rounded this off to the nearest tenth? 45.9, but I got to round up, 46.0 degrees. So B is 46.0 degrees. Now, how do I find C? Well, I've got two angles. Now, this is only approximately, I admit. So I'm only going to find C approximately, but I've got it as accurate as I want it. So what's 74 plus 46? 120, approximately. 180 is the whole triangle. 180 minus 120 would be approximately 60. You could do the law of sines a second time and find that C is approximately 60. But remember, once I have two angles, I have the third. So here's the law of sines and the law of cosines working together to solve a triangle. Okay, I'm going to just give you one example there because I want to go on to some funny area formulas for triangles. Move that over there, slide those papers up, get that out of my way. Let me show you two funny triangle area formulas. And one that you already know. And they're useful at different times and different places. Now this is from in our work this week. Excuse me, back. This right here is section 7.4. What we just did was section 7.3. So 3 area formulas for triangles that you can use. The first area formula for a triangle, ABC. Now remember, this is little a, little b, little c. But the first famous triangle formula you learn, maybe the first formula you ever learned in geometry class, is 1/2 base times height. And the problem with this formula is not terrible, but the problem with this formula generally is you can identify any one of the 3 sides as a base, but it's not easy to find out what the height is. To find the actual height of the triangle, it's not one of these other sides. Excuse me. So if you call that base B and height H, the pain of using this formula is that you have to work out the base and the height by yourself. That's not to say you can't. You know, if I said to you, here's a triangle, and this side is 10, and this angle is 70 degrees. What's the area of this triangle? Well, you could find the height by using your trigonometry. You'd have to know what this third side is, but you could say H is to be as the sine of 70 degrees. So the height is B times the sine of 70 degrees. Now I got to be careful. I'm using B here for side of triangle, not for base. And then the area of this triangle would be 1/2 base 10 times height B sine 70. But you see your problem right here. Excuse me, I got to get my paper centered. You still have to find B, or else you're out in the cold. So here's the first formula you ever learned about a triangle in general. Let me get my book and show you another formula that's useful. Section 7.4. What if I knew all 3 sides of the triangle? Let's draw a new triangle, ABC. Let's call this side A, side B, side C. What if I knew all 3 of these numbers because I had solved the triangle? Like in the last problem, 12.7, 17.0, and 15.3. Can I use the 3 sides to find the area without talking to the angles? This is called ancient Greek person, Heron's formula. Heron's formula says, if you know what A, B, and C are, just take half of that. Remember, A plus B plus C is a perimeter. So Heron's formula says take half of the perimeter and you can calculate the area by taking this semi-perimeter. People call it the semi-perimeter. Semi means half. Semi-annual means once every half a year. You can take this semi-perimeter and take that number S times S minus A times S minus B times S minus C and take the square root of it, and that'll give you the area of this triangle. That's a fancy formula. In the book, he shows you how to create this formula. I'm not particularly interested in how to create this formula, but let's do a demo on this problem. Let me slide this problem together. So could I figure out the area of this triangle just by referring to the 12.7, the 17.0, and the 15.3? Remember, 17.0 is an approximation. So my answer is going to be an approximation. But I do know the perimeter. 12.7 and 15.3 is 28, plus 17 is 45. So in this triangle, I can say that the semi-perimeter, the perimeter is 45 when you add these three together. So the semi-perimeter is 1/2 of 45. 45 over 2. Let me slide this paper out of my way. 22.5. You know, if this didn't come out to be an exact answer, I'd be using decimals anyway. But now take 22.5 and subtract A and subtract B and subtract C, multiply them, and take the square root. 22.5 times 22.5 minus 12.7. This is not like quick. 22.5, and we're getting to the top of our time, minus 15.3, and 22.5 minus 17.0, and then take the square root. Now, I'm going to let the calculator work out these numbers, even though it'd be a long thing to type in. All I got to do is take the square root of this whole mess. I could do the subtraction, right? Although I'm not excited by that. That would be 9.8. Minus 15, that'd be 7.2. Minus 15.3. Here, this would be 5.5. So I could take 22.5 times 9.8 times 7.2 times 5.5. But I could also just type this in as I wrote it. Let's bring the calculator over. Let's slide this paper over. How do we get them all in at once? Let's try that. So clear, square root of 2.5 times 9.8 times 7.2 times 5.5. Calculator says 93444410094. Now, remember, this is just an approximation. So my side links were given 3 digits, 12.7, 15.3, 17.0. I think I'm going to cut this off at 3 digits. The area is approximately 93.4 square feet. If you have units of feet for your length, then the area is square feet. If you like, you could go and work out the height here and do the sine or the cosine to tell you what the angle between these is. The 1/2 sine, sorry, the 1/2 BH, the height is going to be the sine of one side times that. So you can expand this, you can use your trigonometry and see if it matches 93.4 feet. It does match. But I got to call it a day here. Now, the law of cosines is really important. We illustrated how to use it with the law of sines. This area formula, Heron's formula here. Okay, it's kind of a cute, fun formula, but it's not necessarily quicker than anything else because you got to work out the perimeter. You got to work out these numbers. So usually I tie things down to 1/2 base times height. There's another formula I use frequently that he doesn't show you in the book. Maybe I'll show it to you next time. If you know the coordinates of these points, like where they are on a grid, then you can also do a quick calculation to find their area. But I'm not going to cram this into 1 minute here. Okay. This is Monday, November 23. I'm not going to see you again till Monday, November 30th. You guys have a blessed Thanksgiving, and however you can celebrate it or whoever get to celebrate it with, stay safe, enjoy your family, what you have, family and friends available to you, and be thankful even if it's not like the most awesome circumstances. So thank you. You guys have a good Thanksgiving, and I'll see you next Monday.